Optimization is a part of life. Whether you're a company that wants to minimize its costs, or a person who wants to maximize your happiness, we all have an inherent desire to make our world the best that it can be. And calculus can help you accomplish that goal. Imagine for a moment that you're at a baseball game. It's the bottom of the ninth, bases loaded. Your team is down 3 runs, 2 outs, 2 strikes. Oh, and by the way, you're at bat. You want to hit that ball as far as possible so you can get a home run and win the game. No pressure, right? What do you do? Well, we can begin to answer this question by appealing to physics. Thinking of the baseball as a simple projectile under ideal conditions, its trajectory will be in the shape of a parabola. And it's possible to show, though I'll spare you the details, that its horizontal range is equal to v squared times the sine of 2 theta divided by g. V is the velocity of the ball after it's hit, theta is the angle from the horizontal at which it's hit, and g is the acceleration due to gravity. If we assume the ball gets hit at, say, 90 miles an hour, which is 132 feet per second, and then we use 32 feet per second squared for gravitational acceleration, then we get 544.5 times the sine of 2 theta for the range of the ball. All we need to do now is find the angle that makes that range as large as possible. Here's the graph of the range of the ball in feet as a function of the launch angle in radians. What we're looking for is what's called a local maximum, or sometimes relative maximum, of the function. Essentially a point of the graph where the y value is greater than everything in its immediate neighborhood. Now, think about what we just talked about last lesson, using the derivative to talk about the shape of a graph. Here, the graph is increasing until we reach the local maximum, and then decreasing afterward. But what's happening there right at the peak? If you were to zoom in close enough to that maximum until the curve looks like a straight line, that line would have a slope of 0. It would be horizontal. So if we could figure out where the derivative is 0, we could know where and what that maximum is. Okay, let's differentiate r of theta. The derivative of sine is cosine, and the chain rule gives us an extra factor of 2, so we end up with r prime of theta equals 1089 times the cosine of 2 theta. Now, what angle theta will make r prime come out to 0? Well, that's going to happen if the cosine of 2 theta equals 0. If you think back to your unit circle, remember that the cosine of pi over 2 is 0. So we must have 2 theta equals pi over 2, or theta equals pi over 4 radians, or 45 degrees. Remember, we always use radians when we're doing calculus, but we can always convert our answers to degrees afterward if we need to. If we plug that back into our range function, we find that if we manage to hit the ball at an angle of pi over 4 radians, it should achieve a maximum range of 544.5 feet. By the way, for comparison, the longest verifiable home run in Major League Baseball was about 575 feet by Babe Ruth, so we're at least in the right ballpark, if you'll pardon the pun. One other note on terminology, by the way. Just to make things more clear, we can call pi over 4 the maximizer and 544.5 the maximum. In other words, the maximizer is the input that gives us the maximum output. It helps to have words for both of these things so we can tell them apart and be clear about what we're talking about. So we found that the maximizer of our function happened at a critical point, an input for which the derivative is 0 or sometimes undefined. The same is true if you're looking for where a function has a local minimum. The minimizer will also always be at a critical value of the function. Actually, that brings up a potential problem. If we have a critical value of a function f, how do we know whether it gives us a maximum or a minimum without knowing what to expect ahead of time? Just knowing that f prime is 0 or undefined isn't enough on its own. But we do have a couple of things we could do. One option is we could make a sign chart for f prime and look at what happens to the sign of f prime on either side of our critical value. If f prime goes from positive to negative, then f goes from increasing to decreasing, and we do in fact have a maximum. But if f prime goes from negative to positive, then f goes from decreasing to increasing, and instead we have a minimum. Actually, these aren't the only possibilities either. We could run into situations where f prime is, say, positive, touches 0 for a moment, but then goes right back to being positive. That gives us a graph where f is increasing, levels off for a moment, but then goes right back to increasing again. Think like the graph of x cubed. This is sometimes called a saddle point, though you'll more often see that terminology in multivariable calculus, which, by the way, you should totally take if you ever get a chance. It's really cool. Anyway, by looking at the signs of f prime on either side of a critical point, we can tell whether that critical point is a maximum, a minimum, or neither. We can also use the second derivative to our advantage to figure out whether a function has a maximum or a minimum. Think about what the second derivative tells us about the shape of a graph. It tells us the concavity. So if we happen to know that f prime equals 0 and that f double prime is negative, that means f is concave down. And if you think about the shape that makes, our critical point must be a maximum of the graph. On the other hand, if f prime equals 0 and f double prime is positive, that means f is concave up. And if you think about that shape, the critical point must be a minimum of the graph. But what if f prime and f double prime are both 0? Well, in that case, it turns out the second derivative test is inconclusive. It can't tell us one way or the other whether f has a maximum, a minimum, or potentially neither. So there's a trade-off here. The second derivative test is often faster, but it might fail. But in that case, we can always fall back on the first derivative test. Let's try out the second derivative test on our baseball problem. Taking the derivative of r prime, we get r double prime of theta equals negative 2,178 times the sine of 2 theta. And if we plug in pi over 4, we get negative 2,178. Since r double prime is negative, r must be concave down in that neighborhood. And that confirms that the critical point we found must indeed be a local maximum. Okay, that just about settles it, right? 45 degrees, best possible launch angle for a baseball. Actually, not quite. See, our model had some simplifying assumptions. There are a number of other factors we left out, the biggest one being air resistance. Any object moving fast enough through the air will collide with air particles that'll slow it down. So actually, 45 degrees isn't the best angle to hit the baseball. Well, dang, I guess all our work was for nothing, right? Not so fast. It did give us a starting point at least. And once you've solved a simplified version of a problem, the next step is often to start introducing those extra factors you didn't consider before and see how they affect the solution. Using those more sophisticated models, you can find that the best angle is actually closer to 30 degrees, which has been supported by actual data from home run hitters. And calculus is still involved. The solution isn't as pretty. In fact, there's no way to write an algebraic formula for the range anymore once you throw in air resistance. It has to be done numerically using computers. But the idea of how the derivative relates to maxima and minima still applies even in that more complicated model. And at the end of the day, with the right tools and the right understanding, you can take any problem about finding a maximum or a minimum and hit it out of the park, so to speak.